Got it. Okay, so I'll be quick. My name is Scott Denning. I'm a professor at CSU, and I'm going to talk to you today in quite general terms about climate change. I call it the 3 S's of climate change, and you see them up there. They are simple, serious, and solvable, and I always use all 3 S's. The middle one is sometimes called scary, and it's sometimes called by other things that start with the letter S, but we will always get to solvable. I don't like to just leave you hanging with that middle S, because that kind of sucks the life out of you. So simple, serious, solvable. Let's start with simple, and it's kind of weird because I've been doing this for like 30 years. You might wonder if it's so simple, how come I still have a job? How come we're still working on this? But let me ask you some simple questions about climate, because it turns out you already know how climate works more than you may think you do. Do you ever wonder why day is warmer than night? Or why summer is warmer than winter? Or why Phoenix is warmer than Fargo? No, you probably didn't wonder these things because you already know. But if you think about it just for a second, you'll realize that the answer to all these 3 questions is the same. The reason why all these things are true is because when you add heat to things, they warm up, right? So we can do budgets. I guess you guys do budgets, and you can do a budget for heat, right? Heat in minus heat out equals change of heat. I don't know if you guys have noticed, but it's a snowy day out there. It seems like it's always snowing when I want to talk about global warming with politicians. But the fact that it's cold and snowy this week and it was warm and sunny last week, that's not climate change. That's because the warm air that was here last week blew away somewhere else, like Kansas or Oklahoma, and it was replaced by other air that came in from someplace else. That's heat coming in and out the sides, right? But when you look at the world, the whole Earth, there are no sides. The world is round, and so sideways movement of heat doesn't change the climate of the Earth at all. It only moves the heat that we've got around to different places. The only way that the Earth can exchange heat with the rest of the universe is through the top. And you don't normally think of the Earth as having a top, but the top of the atmosphere is what I'm talking about. So the heat coming in and out of the Earth has to come in from the top. Can't come in from the sides because there's no sides on a round ball. The heat coming in to the top, we all know about that. That's the sun. But if that was the whole story, remember I said heat in minus heat out equals change of heat. That's just heat in, heat in, heat in. The Earth would get hotter and hotter and hotter until something terrible happened, right? The world would melt or boil or vaporize, or that hasn't happened. So that can't be the whole story, and it's not the whole story. There's heat going out through the top, but you can't see it. You can see the sunlight, but the heat getting out is in wavelengths of the spectrum, the radio spectrum, that we can't see. They're called infrared rays. And that heat going out to space has to balance the heat coming in from the sun. Has to be. And it's true. You, me, the wall, the floor, the ceiling, everything emits infrared heat all the time. And the hotter something is, the more infrared heat it emits. Now, the outgoing heat has to get through the air. You knew there was going to be some science in here. Here we go. So these are molecules of air. Okay, 99% of the molecules in the air are just these 2 kinds. That top one is oxygen. You guys know about oxygen, right? If you don't know about oxygen, hold your breath for a minute and you'll figure it out pretty quick. The other molecule that's the rest of the air is nitrogen, N2 and O2. And these are 99% of the air. What's the same about these molecules is that they're 2 atoms of the same element, kind of glued together with these shared electrons. You learned about this in high school with the chemical bonds that hold these things together. And infrared energy is going out through the atmosphere. It's waves. Again, we don't really have time for that. They told me to talk for 15 minutes, so we're not going to get into electromagnetic theory. But you can imagine waves of electric and magnetic energy going through space. And remember you learned about electrons have negative charge. Those little horizontal lines supposed to be electrons. The magnetic field can grab a hold of those electrons and accelerate them. And you wind up actually getting vibration along the bond. The molecules get longer and shorter, like woo, 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 woo. They don't really make that sound. I just make that part up. But the vibration of that molecule has now absorbed some of that energy that was going out to space and transformed it into the vibrational energy of the molecule. So that's actually energy that is no longer going out to cool the Earth. It's now trapped, and the molecule can de-excite. Goes from this vibrational woo to a slower vibration, whoa, whoa, whoa. It's ground state, and that energy is re-released as a photon. That's that's electromagnetic absorption by these gases and in emissions. But because 99% of the molecules of the air have just 2 atoms, this is the only dance they know. It's the only way you can change the geometry of a 2-atom molecule is to make it longer and shorter like that. There's a couple of other gases in the atmosphere. That top one is carbon dioxide, the bottom one is water, and these together constitute less than 1% of all the molecules in the atmosphere, but there's more ways to wiggle these guys than there are the O2 and N2. So I only got the 2 hands, so let's let this be carbon, oxygen, oxygen. And the CO2 molecule, just like the O2 and the N2, can absorb that radiation and go woo, 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 or back to its ground state, whoa, whoa, whoa. But there's more. Because unlike O2 and N2, it can go each one of these different ways of wiggling this molecule will absorb a slightly different wavelength of infrared light, a slightly different energy level of photon, and that's what makes CO2 a greenhouse gas. Water vapor is even better. It's got that bend in it, kind of this thing and this thing and this thing. They told me to stand by the mic or I would, get out here and never mind. So you can see that there's more ways to rearrange the geometry of a 3-atom molecule than a 2-atom molecule, and that's what makes these greenhouse gases. It's not because of capitalism or Al Gore or anything like that. It's just bad luck that the gas that comes out when we set carbon on fire has 3 atoms instead of 2 atoms. It can therefore absorb and emit infrared radiation better than the 99% of the air that doesn't have 3 atoms. So that's the story. You've all seen the cartoon, right? The sun beats down on the earth, some of it reflects off. The part that doesn't reflect off gets absorbed. That's what keeps the earth warm. The earth's got to get rid of all that heat by radiating out to space, but the outgoing radiation gets stuck. It gets caught by these wiggly molecules up in the sky and re-radiated down on us. If you go around with a radiation measurer device, which I have one in my office, didn't think to bring it, you can measure the radiation coming off of things. If you point that sucker up at night, there's no sun, but there's still radiation coming down to the surface of the earth at night. About 300 watts of radiation per square meter of ground, and that's what keeps the earth from freezing solid and, the oceans turning into a ball of ice and all of us dying. I mean, it's a good thing that the greenhouse effect is there, but adding CO2 to the air enhances this greenhouse effect, makes it stronger. So brings me to what I call the common sense explanation of this problem. You guys, most of you probably old enough to remember these things. These are incandescent light bulbs, and this particular one is a 4-watt light bulb that we used to have, back when I was a kid. They were Christmas tree lights, and then when my kids were little, they were night lights that you helped find the bathroom at night. 4 watts. If you double the amount of CO2 in the atmosphere, you're adding this much extra heat to every square meter. Okay, this podium is about a half a square meter, so imagine a, light bulb there, but also there and there and there and there and there and there and there, but not just this room and not just Colorado, but the entire planet covered with little 4-watt light bulbs every square meter, and you're going to leave these light bulbs on 24 hours a day, 7 days a week for the rest of your life. Now, if you did that, the Earth would be a little bit warmer. And we're not talking about a lot warmer because they're only 4-watt light bulbs, but there's a boatload of them, right? These things are every 3 feet covering the whole planet. That's the amount of extra heat you get from CO2, from doubling CO2. Believe it or not, all of that was known before light bulbs were invented. This is not something that we discovered after the world started warming up and we wondered why. This was discovered back in the 1860s when Abraham Lincoln was president. This guy, John Tyndall, measured the absorption of radiation by CO2, measured different wavelengths of it, measured how much the radiation is absorbed depending on how much CO2 you put in these little glass flasks that he had in his lab in the 1860s, and predicted that if we kept burning a bunch more coal, this is 150 years ago, that it was going to warm the world. So the biggest myth that I encounter about climate change is, quote, scientists expect it to warm up because it's been warming up lately. And it has been warming up lately, right? Everybody's seen graphs like this, that back in the day it was cooler and then it warmed up and now it's been warming up faster. But that's not how we figured this out. We did not look at graphs like this and decide that global warming was due to CO2. No, we know that when CO2 is added to the atmosphere, it'll warm up because we know that when you add heat to things, they change their temperature. Okay? That's formally called the first law of thermodynamics, but you got to be some sort of egotistical Victorian Brit to call something that simple the first law of thermodynamics. I mean, for God's sakes, cavemen knew that, right? They put the mammoth on the fire and it got hot. But they didn't say, first law of thermodynamics. They said, ugh, hot. Okay, so that's it for simple. Now comes the middle part. I got to tell you that this is deadly serious. And nobody likes to talk about this part, but we got to face it. And there's no soft pedaling it. This is a problem that gets worse and worse and worse until you stop making it get worse, and then it doesn't get better. So if you let it grow, eventually it becomes the biggest problem there is. And we mustn't do that. I want to talk to you a little bit about how much warmer it's going to get. These are 3 estimates of warming in this century for a low emissions future, a medium emissions, and a high emissions future. And the different colors on the map are different temperatures in the future. So obviously the biggest thing is the more CO2 you emit, the hotter it gets. But if you look a little more closely, you notice that the maps are not all the same color. And that means it doesn't get the same amount of warm everywhere. So the biggest, most obvious thing is that the land warms up a heck of a lot more than the oceans. And that's because the oceans are really deep. On the average, the oceans, you probably don't know, on the average, the oceans are 13,000 feet deep. And you can imagine, if I put a 4-watt light bulb on 13,000 feet of water, it's not going to warm up very much, because there's a whole lot of thermal mass in 13,000 feet of water. But the land doesn't have that. So the land warms up way more than the ocean, and if it's going to warm up a certain number of degrees, it warms up way more degrees on land than it does in the ocean. The next thing, if you look, the southern hemisphere doesn't warm up as much as the northern hemisphere. That's because the southern hemisphere is mostly ocean, and the northern hemisphere is mostly land. The third thing, if you look even more carefully, is the places with snow and ice warm up more than the places that don't have snow and ice, and that's because snow and ice is bright and white and it reflects the sun to space, and if you warm up enough to melt the snow and ice, then you soak up extra sunshine, and that gets added to the 4 watts that you get from the CO2. So if you happen to live on land in the northern hemisphere where it snows, you get extra. You don't just get global warming, you get about global warming and a half. And of course, that's right where we live, is in the northern hemisphere on land where it snows. So if you look at the middle of North America, up in there in that low emissions world, it's about 3 degrees of warming. In the high emissions world, it's about 6 degrees of warming. But oh, wait, those are Celsius degrees, because science, right? So if you want to convert that to the kind of degrees that you and I work with every day when you look out the window, to Fahrenheit degrees, you got to multiply by about 2. It's 1.8, right? So go from Celsius to Fahrenheit. So instead of 3 to 6 degrees of warming, we're looking at 5 to 10 degrees of warming for the middle of North America, depending on how much future emissions. Now, even 10 degrees doesn't sound that bad. What is it, like 33 degrees outside today? 10 degrees warmer would be 43, and I would probably be fine with that. But we're not just talking about today. We're talking about, on the average, 10 degrees Fahrenheit warmer. And you don't really have a good sense of what 10 degrees Fahrenheit of warming looks like until you look at a map. This is a map of average high temperatures in the United States in Fahrenheit, and each color on the map is 5 degrees Fahrenheit. And I got a dot there for Denver, and I got some other dots for other cities. And what we're going to do is going to move each of those dots by 2 colors on the map to simulate 10 degrees Fahrenheit of warming. And you see that 10 degrees Fahrenheit, why isn't that doing anything? There we go. 10 degrees Fahrenheit of warming is a lot. 10 degrees Fahrenheit is like moving from here to Albuquerque. And if you moved from here to Albuquerque, you would notice, right? If you were a farmer in eastern Colorado and you swapped out the climate of Albuquerque for the climate of the eastern plains of Colorado, you would absolutely notice. You would not be able to grow the same crops. You would certainly need more water. You'd need more water for your cities. You'd need more water for your lawn. You'd need more water to do just about anything around here if we swapped out the temperature of Albuquerque for the temperature of Denver. Around here, when we think of temperature differences, it's not so much latitude, it's altitude, right? We think of where is the nearest cold place? Up in the mountains, right? So the mountains actually cool off about 10 degrees Fahrenheit for every 3,000 feet of elevation. So if I tell you it's going to warm up 10 degrees Fahrenheit, that's like moving from here to Estes Park. Or the other way around. It's more like moving Estes Park down here. It's like moving Trail Ridge Road down to Estes Park. So 3,000 vertical feet of climate change is a huge amount for around here. Now, back at the end of the last ice age, those climate zones marched up the mountain, right, as it warmed up. But it took 100 centuries for 10 degrees Fahrenheit of warming to happen here at the end of the last ice age. And we're talking about doing it in 1 century. So it's a similar kind of warming to what happened at the end of the ice age. It's like swapping out, you know, Estes Park for Denver climate or Trail Ridge Road for Estes climate, but 100 times faster than it did the last time. This is pretty serious for us in Colorado. We happen to be a region on the edge. We live in a place that's very vulnerable to warming because of the water. This is a map of the western United States, the average precipitation that falls in the western United States. 75 million people live on that map. And you notice that on the map it's mostly brown. Actually, if you ever drive, you know, from here to California, it's mostly brown. But the reason why we can support 5.5 million people in Colorado or 75 million people on that map is because of those blue places on the map. You know what those blue places are called? Mountains. So the mountains reach way the heck up in the sky and they gather the water vapor as it flows past. They turn it into snowpack. And that's our water supply. Our water, almost all of our water comes to us from melted snow up in the mountains, and we bring it down and we put it in our reservoirs, and then we pipe it into our cities and our towns, and we irrigate our agriculture with it. And over the last 50 years, the small amount of warming, we've only got 5 more minutes, okay. Small amount of warming we've had have already knocked off about 20% from our peak snowpack in Colorado, and that's only about 2 degrees Fahrenheit of warming. You can do the math yourself. If 2 degrees of warming knocked off 20% of the snowpack, what does 10 degrees of warming do for your snowpack and your water supply? But water budgets are not just about water in, they're also about water out. Just like heat in minus heat out equals change of heat, water in minus water out equals change of water. And the hotter it is, the more water evaporates from our land. The more water you need for your lawn, the more water you need for your farms. So hotter air also increases your water demand. So unless your precip keeps up with that, it's a problem. Now, I'm going to have to skip some. These are scary slides anyway. You didn't want to look at them. I want to say something, because I know Liz is going to talk in a minute about buildings. I want to say something quick about buildings. These are some graphs of projections of energy use in buildings in the United States. That top one is a projection out to 2030 made in 2005 by the U.S. Department of Energy. Then the next one is from a projection made in 07, 09, 11. And you see what's happened here is basically over the last decade or so, the amount of energy we expect to use in our buildings has fallen dramatically. That's because we've gotten smarter about how to make energy efficient buildings. And just that one change alone is expected to save U.S. Consumers $4.5 trillion over that period in energy that we don't need to waste anymore. So this doesn't have to be a killer cost. This can actually be a huge savings for us. And I want to talk very briefly about costs. Converting the whole world off of fossil fuel and onto other kinds of energy is projected by economists to cost about 1% of the global economy. Now, you guys are Denver politicians, and you probably don't know what the GDP of the world is, but I'll just tell you. It's about $75 trillion a year. And 1% of $75 trillion a year is a lot of money. It's about $750 billion a year. So this is a lot. That's more than the U.S. spends on defense. It's a big number. 1% of the global economy is about what it cost my grandparents' generation to retrofit all the world's cities with indoor plumbing. Think about that. Think about what it would cost to dig up every street in New York and London and Paris and lay sewer lines, and to knock out every tenement wall 20 stories high and put in hot and cold running water, and to knock out all the partitions and all the flats and put in sinks and toilets and showers. And oh my gosh, are we glad they did that, right? Because would you rather the world economy was 1% bigger and you still had to poop in the street? So not only that, imagine what it did for plumbers. Imagine what it did for plumbing suppliers. Imagine what it did for the grocery store down the street from the plumber, or the children of that plumber being able to go to college because of the income that came from building all that infrastructure. These are my grandparents. That's Max and that's Florence. And it was their generation, it wasn't them personally, but their generation that did that indoor plumbing. And when they were done with indoor plumbing, they did rural electrification and subways and fought the Nazis. These people were no slouches. These are my parents. That's Margie and Bob. And their generation They did a bunch of great big things too. They built the interstate highway system. They fought the Cold War. They sent people to the moon, for goodness sakes. This is me and my wife back when I had hair. Our generation invented the PC. We built the internet. We replaced billions and billions of landline phones with these little machines that cost, you know, $200 a month for my family with the data-hungry teenagers. And it was totally worth it. We spent 1% of the global economy on every one of those projects, and the global economy didn't go bust because we built cell phones and the internet, right? The global economy did fine. We made the world a better place, and we got rich doing it. These are my children. That's Matt and that's Nate, and they get to do it again. They get to replace an energy system that's destroying the economy with one that will be much better, which will lead to better outcomes, and which will generate all of the employment in their generation. You can choose the way you think about history. This is coal. And there's a lot of people think that our well-being comes from stuff we dig out of the ground. There's value in the coal. You sell it to make energy. You sell the energy to make products and services. And pretty soon you got a $75 trillion a year global economy. And maybe that's right. But I hope that it's not that simple. Because if that's the real story, when we stop burning coal, we're going to freeze in the dark. I prefer to think that we make our world. That it comes from creativity and ingenuity and hard work. Not from the ground. It comes from what's between your ears. And we're not running out of that stuff. As long as our kids can be as hardworking and as ingenious as our ancestors, they're going to be fine. Thanks for your time, and I'd be happy to take your questions.